Are you feeling lucky today? You should be. If it hadn't been for a coincidence so great that it should never have happened in more than 10 to the power 56 universes, you would not exist today at all. According to our best physics predictions, dark energy density ought to have been high enough that stars and atoms would have been torn apart from its strength, unable to coalesce through gravity. Stars shouldn't exist, nor should planets, nor should you. As it happens, the actual density of dark energy is much, much lower, to the point that allowed us to exist, which is a fortunate coincidence, and raises the question, was this truly chance? Some argue this hints at the existence of a god, or an alien race so advanced that they might as well be gods, who created the universe and set its values in just the right way so that life would arise. But in physics, another theory has developed, one that says the best answer to this great cosmic enigma is the existence of multiverses. Does your being here prove that multiverses exist? Why do some physicists believe this idea? And what might other universes look like? The topic of them. In our last video on this topic, we laid out the foundation of what is known as the cosmological constant problem. It notes that some force, dark energy, is prevalent enough that in our modern day it overpowers gravity on a grand scale and is causing our universe to expand. This dark energy density is at a convenient level. If its density, tied to something known as the cosmological constant, was much higher or much lower, then our universe would either have been ripped apart by dark energy gone rampant, or would have collapsed down to a singularity due to unopposed gravity long before life had a chance to get going. The problem in this is that our quantum models predict that the density of dark energy really ought to have been higher. How much higher? Somewhere between 10 to the power 56 and 10 to the power 120 times higher than it is. That's more than a little off. That's so far off, it's been called the worst theoretical prediction in the history of physics. But the quantum field model is very correct in other ways, whether it's the double slit experiment with a single particle or the Bell equality test. Quantum physics turns out accurate predictions for some of the weirdest effects that we see in our universe. So how do we account for this discrepancy? Those of a religious mindset would point to the idea of intelligent design, that this wasn't so much luck as intent. A god, or extremely advanced being, has set the value of dark energy density to be just right for life to come into being for the purpose of creating us. Of course, this idea doesn't sit well with everyone. The existence of a god-like being by nature is difficult to prove or disprove, and taking such matters on faith is not really what science is about. For many scientists, a different sort of answer was needed. This is where multiverses start to come in. Let's go back to 1987, when the precise value of dark energy density in our universe had not yet been measured, but it was clear that it was extremely small, or zero, since, well, we existed, and so did everything around us. That year, physicist Steven Weinberg published a paper connecting the universe's fortuitously low dark energy density with something known as the anthropic principle. Essentially, the only universes that we can evaluate the probabilities of are the universes that met the right conditions to produce us. If the universe hadn't rolled such an unlikely roll of the dice, there would be no us to say whether these things were more or less probable. If it takes a massively unlikely roll of the dice to produce humans, then a universe where that roll of the dice actually happened is the only universe we could possibly see. Weinberg could be more specific than that. He was confident that the threshold of dark energy density for forming life would be no lower than the threshold for forming galaxies. In other words, by the time galaxies have formed, you've probably crossed the threshold to where life can form too. After all, how else was life supposed to arise if there were no stars and galaxies to provide complex building blocks and energy? At the time of his publication, observations of an extremely old and distant quasar had indicated that galaxies had already begun to form just 1 billion years after the Big Bang. Weinberg used this information to calculate that the formation of these ancient galaxies required the dark energy density to be smaller than around 10 to the power minus 7 joules per cubic meter. That meant that, assuming the galaxies were indeed necessary for life to arise, the threshold dark energy density for life to exist was less than or equal to this value, while not being so low as to be negative. Weinberg initially reasoned that if the dark energy density was significantly smaller than this value, something else other than anthropic reasoning must explain the dark energy density smallness. However, as we now know, the real dark energy density is closer to 10 to the power minus 9 joules per cubic meter, which isn't too far off from the threshold of 10 to the power minus 7 calculated by Weinberg. In short, life and dark energy density correlate surprisingly well. Of course, this ignores one vital point. Just because we can see universes where we exist doesn't mean it is guaranteed that we should exist. We could have just not existed at all. After all, the odds of the cosmological constant being at its recorded level is incredibly unlikely. Could the various contributions to the dark energy density have cancelled out to a value compatible with life just by chance? Probably not. Here's what would have needed to have happened. Just imagine generating 3 random real numbers between -1 and 1, adding them up, and hoping that the magnitude of the sum is at most 0.0000 with 55 zeros 1. It sounds just about impossible. But what if we had more than one go at it? What if we could generate those numbers over and over and over again until we got lucky? It might take us something like 10 to the power 56 tries, but given enough time, the unlikely cancellation of 3 randomly generated numbers will turn into an inevitability. We can use the same logic to potentially explain why the dark energy density is so bizarrely small. Instead of just one universe, imagine there exists a vast multiverse, with each universe having a different, random value for the dark energy density. Only a tiny fraction of them would have a dark energy density small enough to be compatible with life, but that's exactly where we humans would expect to find ourselves. This explanation requires no coincidences, no fine-tuning, no intelligent design, just a lot of different universes. On its own, the idea of a multiverse would still be too vague to be good scientific theory. For starters, what kind of multiverse are we talking about? How do they exist in the first place? Fortunately, there are actually a few different concepts of multiverse that physicists can describe. Firstly, we have a multiverse separated by time. If you are familiar with the idea of the Big Bang and the Big Crunch, you will know that it's often believed that this creation and destruction of the universe is an eternally repeating process, with new universes arising each time. If the underlying numbers of each universe are a bit different with each iteration, for instance, if dark energy density can change from universe to universe, then with enough Big Bangs and Big Crunches, you could inevitably end up with a universe with a dark energy density exactly like our own. There are a few assumptions at play here, of course, as we don't know for sure that the universe does contract into a Big Crunch yet. But if it does, and if the rules of the universe are a bit different with each new iteration, then this is a viable model for a multiverse. A second multiverse described by physicists, although one I find personally a little bit more iffy, is a multiverse separated by space. While the rules of physics seem to be consistent across all of space that we can see, there are realms of space beyond our sight, sections of the universe that are accelerating away from us so quickly we will never see light from them. It's conceivably possible that the rules of these parts of the universe could differ from our own. And if this occurs, then we are essentially in another sort of multiverse. I find this model a little less satisfying though, both because it feels strange to call a further away part of our universe a different universe just because we can't see it, and also because there is no evidence that the laws of physics differ across space. This seems to me to be the least likely sort of multiverse. But finally, modern physics describes a third type of multiverse, one that is disconnected from our space-time entirely. In the many worlds interpretation of quantum mechanics, every macroscopic interaction or measurement of a quantum state causes the wave function of the universe to branch into multiple non-interacting parts. If you've heard of Schrödinger's cat, you can imagine the universe splitting into one universe where the cat is alive and one where the cat is dead. With every such interaction, the total number of universes grows exponentially, and the quantum multiverse becomes even richer and more diverse in its features. To be clear, we still don't know whether this branching process is the correct physical description of quantum mechanics, but it is arguably the simplest, and it is perfectly consistent with all experimental data. Or rather, we have no proof that it doesn't exist that way. If it does turn out to be correct, then it would add a whole new layer of complexity to our understanding of the multiverse. Multiverses are useful in that they remove the need for massive coincidences or intelligent design as a way of explaining our presence in the universe. However, are they actually real? Unfortunately, the answer is an unsatisfying "we don't know." While differing multiverses do help solve the cosmological constant problem, we actually have no evidence that they exist beyond the offering of an explanation for that coincidence. We have no proof that the laws of physics change across space or time or quantum universes. If other universes exist, they might have exactly the same laws of physics and values for dark energy density as our own, which would put us right back in the same problem we started with. How are we here when the odds of the galaxy itself existing is 10 to the power 56 to 1? And getting that proof will be difficult. We will need to either survive through a big crunch, or pass into a part of the universe that's so far away that not even light can travel quickly enough to get back from it, or enter a different quantum universe somehow. All seem impossible, or at least very difficult, and potentially the kind of trip you can't return from. This might be just as unprovable as the existence of God. So, in a way, you are free to believe whichever you find most comforting, or perhaps continue to wait until a better way of answering the question can be found. What is undeniable is that we are here. We live, we breathe, we can experience all the joys of life. However that came about, that's something to be incredibly grateful for. If we keep striving, perhaps we can one day discover the secrets to our origins. Whether we got incredibly lucky, did an all-powerful hand guide us into being, or was it the rolling of infinite dice that caused an inevitable result? Believe what you like. Just don't let it stop you from appreciating the wonders all around you. We don't need there to be a multiverse to appreciate this universe we're in, after all.